and it's recording. So we'll just minimize that. And we'll start with our pen. Lesson 1. And let's first of all talk about the carbon atom. And why carbon is so special to begin our lesson. Essentially, carbon has an electron configuration of 2 in its first orbit, and then 4 in its outer orbit. And this is the part that really matters, the outer orbit. So if we look just at the outer orbit, carbon, we can draw a Lewis picture where it shows those 4 outer electrons. Those are the ones, of course, that interact with the rest of the world. So the chemical bonds of carbon are formed with these 4 electrons. Now, having said that, you're at a point in your life where you may, has anybody taken grade 12 chemistry yet? Okay, so some of you know about something called orbital hybridization. And so what we've discovered is that to explain some of the goofy, wacky things that carbon and other atoms actually do, we have to consider that there's more to the story than what these Lewis models and Bohr-Rutherford models show. And what happens is, and I'm going to make this very simple for us for now, is that these 4 electrons in the outer orbit are able to sort of shuffle themselves up with electrons from underneath and create new bonding possibilities. Okay? The other thing that you will have learned is the difference between what's called a sigma bond and a pi bond. Hands up if you've never heard of that before. Right. So you see, the problem is we're trying to learn biology and understand the complexities of biology, but we don't have the chemistry yet. And it's kind of like school is always like this in science, right? It's always back and forth. You're always behind or ahead. Yes, sir.
So wouldn't the smart thing be to have the grade 12 chemistry run first semester and then the bio after?
Yes and no. Yes and no. It's not necessarily to take chemistry before bio, as long as we can sort of bring ourselves up to speed on the small bits of chemistry that are in bio. Most of this course will not require a whole lot of extensive chemistry. It's just the first part with the biochemistry, and that's where we start, that does require a little bit. But we can just conceptualize these things without knowing them in full detail to get the idea. So essentially what this means is that we're trying to use this orbital hybridization, S and P, to explain how carbon makes the bonds it makes. But for us, it's quite simple in biology. If we remember that carbon can make basically 3 different bonds with itself, okay? So carbon can, let's see if I remember how to go down here. Here we go. Carbon can join with itself by sharing one pair of electrons between it. And so this becomes a shared pair here, and we usually write this as a dash, right, for the carbon atom. The problem, of course, is that this leaves the other electrons, which are not shared, wide open. And so this kind of a bond will satisfy one of carbon's requirements, but not the other 3. And so typically, these other bonds have to be joined to something else. And quite often, the filler atom in organic chemistry and biology is hydrogen. And so hydrogens, which bond with one electron, making one shared pair, can sort of fill out the gaps. But we'll get to that in a minute. But the other thing carbon can do is it can bend and twist. Okay? It can bend and twist. So a carbon atom can actually have 2 shared pairs between it. Now when it does this, it creates a whole different shape, because these electron pairs have to sort of bend. And so what happens is you're left with 2 electrons, sort of like this. Remember, the Vesper theory says that the electron pairs will push as far apart as they can. Now, just to give you a quick sort of, because it's AP, right? How about what about S and P orbitals? You all took grade 11 chemistry. So S and P orbitals you know, right? You know what those are.
Yeah.
Okay, so let me try to go down, extend the page. So if you picture a carbon atom, and you picture the orbitals, you know that around the carbon atom, there is the S shell. So let me draw the S shell, and I'm going to draw it with a crayon here, just sort of shade it in. Crayon, let's go blue. So there's this fuzzy region around here, and it's spherical, but on the board it looks like a circle. Okay? But also, see if I can't get this. That's the 1s orbital. Then you have the 2s orbital, which would be on the outside of that, which is further up. I'm going to actually draw it in closer so our picture is not. So there's my 1s orbital. And then there's another shell. It's kind of like the Russian doll thing, you know, where one smaller one is inside all the rest. But when you get to on the periodic table, the first two columns are the S filling columns. That's where the electrons live. When you jump across the boron, carbon, nitrogen, and oxygen, you jump into the P block, right? The P orbitals. P orbitals look like this. First, let me draw them over here. One is sort of like a dumbbell shape like this. The other is a dumbbell shape like this. And the third one is a dumbbell shape that would come out of the board and go into the board, which I can't draw from this perspective. It's like a 3D version. So what's interesting is you can see how a double bond could form between carbon atoms. Let me show you, let me erase that, and then put another carbon atom here. But before I do that, I'm going to draw those orbitals back. So I'm going to put just one. Let's put the p orbital here. Just one of them, to make it simple. When another carbon atom gets close to this, it can do something kind of unique. So let me draw it right about here. The inner S1 orbital is still there. The S2 orbital can interact and form a bond right here. So those two electrons are sharing. But also, because this one has a P-shaped orbital right here, if it's close enough, you can get a bonding or sharing in here. Those p orbitals would actually overlap like this. See that? And so we call the s orbital overlap a sigma bond, S for sigma, and we call the p orbital overlap, P for pi, a pi bond. So that's really just what's going on there. And you can kind of visually see if these two got together, how these ones, because of their shape, could also bond at the same time as the circular ones were bonding, right? And that's how you get a double bond. Now, in order to do this, there has to be a little bit of shuffling of the electrons around a bit. And that's what we call hybridization. And those of you who took it will know about sp3 and sp2 and sp and all of that, which you'll learn about in grade 12 10. All we have to understand is that it can make a double bond. And the key thing is that it changes the shape of the molecule a little bit. Carbon can also make a triple bond. So let's explore that option. We're not going to get into the pictures. You could imagine, though, that if I drew in the pi bonds going in and out of the board, they would also line up together, and they could be forming a second pi bond. Right? When you see the quantum picture, it explains a lot. But again, let's just go back to our symbols here. So we have carbon, 3 bonds. And that would leave only one electron, and it would be sort of over here and over here. Remember, they try to get further away. So right away, what this does is it tells us that there will be shapes, depending on whether you have double, single, or triple bonds between the carbon atoms. The shapes will change. So what we're going to do right now is we're going to use models to show these shapes in 3D, which I can't do on a smartboard. So we're going to pause this recording for a minute. Okay, so we're back. What seemingly was no time at all. And what we want to look at is the fact that carbon atoms bonded to other carbon atoms on the board seem to form a chain. But when you look at them from a different perspective, that chain is sort of wiggle-waggly. It's more like this, depending on which way you look at it, 3D. So we just have to, it's easier to draw it this way. So we have to remember this in our minds when we're watching, looking at things. Now, if you have a double bond in there, a double bond to a carbon, on the board looks nice and straight. But in reality, what actually happens is it sort of kinks the molecule, which causes it to bend, something like that. So double bonds cause kinks and bends. Okay? Double bonds cause kinks and bends in the shape of the molecule. Triple bonds also cause kinks and bends. This molecule would not be a straight line. In fact, when we built the models, we saw that the triple bond bends it very strongly, sort of in that direction. So double bonds, and then also we could add here also triple bonds, make kinks and bends. And you can actually calculate the bond angles, and how much they bend, and what kind of hybridization is required to make it happen. For us, in our biology, all we want to remember is it makes kinks and bends. Because shape is the secret to biology. Molecular shape is the secret to biology. So that's all I'm going to go into with this carbon. And those of you who've taken the chem have a little bit more under your belt. Those of you who haven't, don't worry, it'll all make more sense later when you take chem. But for us, this is not. All right, now let's continue and talk about some of the simple carbon arrangements. When you take organic chemistry, the first thing you learn are the groups of simple carbon arrangements. All right. First of all, let's talk about a group of chemicals called the alkanes. The alkanes are simply carbon and hydrogen. They contain carbon and they contain hydrogen, and that's it. They're sometimes called hydrocarbons. So if you take a carbon atom with its sharing 4 times, well, if you're going to join it with hydrogen, you have to have a hydrogen at each of the shares. And so we get this sort of structural model. Now remember, this looks like a cross, but it's really that tetrahedral shape, that 3D shape that's hanging there in the middle of the classroom. So when you see this, think that to help you remember about the fact that these 2 hydrogens, the one on the top and the bottom, are sort of angled slightly towards you, like this, out of the board. And these 2 would be angled slightly away into the board. Very hard to draw, but we need to remember that. This one is called methane. Methane, that's an A, methane. Most of them will end with ane, and that's how you know they're alkanes. It's quite a simple process. Now, all you do to make the whole family of alkanes is just keep adding carbons. So you put 2 carbons together, and the rest of the bonds are hydrogens. You have this guy. He's called ethane. And then 3 carbons. And then you can see there's a pattern developing, right? We're just sticking an extra carbon in the middle. So this family of elements would now be called, well, this is all the alkanes. This one will be called propane. This is what we power our barbecues. Propane. Ethane is a gas. We don't really use it much in our everyday lives, but I'm trying to think of where you might find ethane in your everyday lives. Ethane, I think, is sometimes used for ripening fruit. No, that's ethylene, sorry. Yeah, poor ethane doesn't really have much common use. Of course, methane does. That's what we call natural gas. That's what's in gas lines. You're running your furnace if you have a gas furnace. Some people have natural gas barbecues, so natural gas is quite common, right? Propane is also fairly common. And so you can go on down the line. The other thing you can also do, I'll just go back a bit, is you can write these in a slightly different form that's a little more convenient, but doesn't give you much structural information. So you can also write this as CH4, right? C with 4 H's. Ethane can also be written as well, there are 2 C's, so C2, H, and if you count them, there would be 6, right? 6. And then if you go down one more, you can write the next one, propane, as C3H, I believe, 8. Propane. And then you just keep on going. So the next one would be 4 carbons, which would be butane, right? So to give you the prefixes, there's methane, ethane, then propane, and then butane. And then it starts to get a little bit normal. There's some pentane, hexane, let's keep going, heptane, octane, which you've heard about if you learned about gasoline and cars, high octane, right? Nomane, and then decane. And at that point, we kind of stop worrying about prefixes because they get so big, they tend to have crazy or other interactions, and they start forming all kinds of circular patterns. Okay, anything past 4 carbons. Let's take a pause and play with the models again just for a second. So I will pause this recording. We will be right back. And we're back. So with the models, we were able to see that once you get sort of around this region, 4 to 5 carbons, it becomes possible for the carbons to make ring structures. 5 is fairly stable. It didn't take a lot of pushing and bending to make 5. To make 4 in a ring required the bonds to sort of be a little bit stretchy and bent. Circle. But that means that that's not very stable. It takes a lot of energy to put 4 carbon atoms in a ring structure. A lot of energy. But not so much to do the 5, the 6. So once you get here and, once you get here and down, 10, down here you tend to see ring structures. So this pentagon ring structure of carbon is going to come up 1,000 times in our course. And this hexagon ring structure shape is also going to come up 1,000 times in our course. And so we want to get to know these. And we'll deal with them as they arrive. Okay, now let's get into these, well, I've been promising, these functional groups. So if I take a long carbon chain, all right, can anybody tell me what this one would be called? This was an alkane. And what's its name? It's 5 carbon alkane. That's pentane. Very good. For those of you who couldn't hear on the video, there was a meek and mild little girl who said pentane very quietly, which didn't pick up. So she was right, whoever it was. Pentane. Now this molecule is, well, I'm going to say it's relatively unreactive. If it floats around, things bump into it, hydrogens are there, everything is kind of sort of even Steven, it's symmetrical, right? It is possible to react. And one of the things that will react with it, of course, is oxygen. And if you put oxygen here, but it won't react automatically. You have to give it a little kickstart to light the match, to give it the energy it needs to start. And then you can burn this quite readily. Propane, this is pentane is actually one of the hydrocarbons found in gasoline. Gasoline is a mixture. Pentane, hexane, heptane, octane, nomane. It's a mixture of those hydrocarbons. And then what they do with the octane each hydrocarbon burns at a different temperature. And so by adding more or less octane, what you can do is you can control the temperature at which the entire mixture burns. And so octane in gasoline is actually used to control how hot we want this to burn. And of course, different engines are designed by engineers to operate at different burning temperatures. Typically, higher performance engines want to burn a little hotter than your Kia, right? So if you're driving a Lamborghini, it might require a 92 octane gasoline instead of an 87, because it needs a hotter burn. The problem, of course, is you have to be careful. If you put 92 octane in a car designed for 87, it doesn't make the car go faster. It doesn't really do anything to the performance of the car that much. What it does is it makes the engine burn hotter. And if it's not designed for that, you will wear out that engine much faster. Things will begin to wear out quicker. So gasoline, there's this weird idea that if you buy the 92, it's better gas because it costs more. It's premium gas. It's only better if you're driving a Lamborghini. It's not better if you're driving a Volvo, right? Or a Honda Civic or something. It's just not good for your car. Anyway, that's an aside. Let's see what can happen if other atoms. Yes, sir.
Question. So I look at pentene here, and they're drawing a structure that's almost like this, and then
Like a pentagon shape.
like that.
Like the wiggle?
Yeah.
Yeah, so what, and that's exactly what this should look like if you were looking at it from the top down. But remember when I showed you the models, if you turn it, it looks all in a line.
Oh, yeah.
So again, that's what I was getting at. We draw them this way because they're easy for simplicity. But depending on the perspective, this particular thing could all, he's basically, for those of you who can't understand because you see nothing happening, he's talking about shouldn't it be this shape? And it would, if we were to alter our perspective and look at it. And so that's something to always remember, and it's a good point. Okay? But for simplicity, we draw them like this because it's just easier, obviously, right? So remember, our drawings are models that give us ideas, but they are not actual representations of what is physically there because they are limited by the two-dimensional board. Okay. Let's see what happens if well, you know what? Let me just use the same picture. This doesn't matter. When you're making notes, you may have to draw it again. I would say draw another one underneath so you can add this next thing to it. But on the smartboard, I can erase and add to it, right? So draw another molecule if you're taking notes. And what I'm going to do is I'm going to erase a little piece. I'm going to basically take this hydrogen off the end. Pop it off. Now, how could this happen? How could you pop a hydrogen off the end of something? Well, I want you to remember the water dance. When things are in water, the negative side of the polar water molecule will pull and tug on anything that's positive. And hydrogen atoms are almost always positive because they're almost always engaged in a polar covalent bond. Right? So in this case, the carbon is hogging its electron a little bit more. That little hydrogen atom then is essentially like a naked proton sticking out on the end. And it will quite easily give up on the carbon and float away and hang out with the water molecule as an H3O+. That water dance happens not just with water molecules, but water also dances with other molecules. And it's constantly putting little hydrogens off of the end of things. And when that happens, that means that it enables another molecule or another atom to jump in. And commonly, we see an oxygen atom stick itself in there, and then we can have the hydrogen atom sort of attached on the end. So that's all we did is we stuck an oxygen atom in there. And just 1 second, I can get this phone going. So this oxygen molecule creates an exciting place on the molecule, this oxygen atom, I mean, where things can happen. There's pushing and pulling of electrons here because of the powerful electronegativity of oxygen. And so other molecules that come in contact with this. This is what we call a reactive site. It's a place where stuff can happen, or at least happen more easily. So typically, when we draw these functional groups, this one is typically drawn. I'm going to erase this for a second. And we don't even put the bond between the O and the H in there. We just write it as OH. And it's called hydroxide. You know that from grade 10. And this OH changes the nature of this molecule. If it has an OH like this instead of just an H, we call it an alcohol instead of an alkane. So alcohols are molecules that have this feature. Yes?
So is alcohol considered a functional group? Is that what you're saying?
What I'm saying is alcohols are a class of molecules that contain the functional group, the hydroxyl functional group. You called them hydroxide when you were in chemistry as an ion, but if you look over the page on page 28, you can see all the functional groups in a chart that we're going to study, and the first one there, and he's called hydroxyl. Because he's not necessarily an ion, right? Because he's just sharing his electron. So when he's an ion with a negative charge floating around, he's hydroxide. But when he's part of a molecule and there's no ionic bonding, he's just hydroxyl. Yes?
So this would now be an alcohol, so we would like pentanol?
That's right. We would call it pentanol, right? If you're doing organic chemistry, that's what you would call it. So, and again, we're not going to get into all the details of organic chemistry. What we want to be able to do is identify this functional group as the hydroxyl group. Now, this is a simple example. So some molecules can have many hydroxyl groups. I'm going to show you an example of the hydroxyl group in a bigger molecule. Okay? Now, here is a molecule, and then we talked, oh, okay, green, why not? This molecule has an oxygen here. So what happens here is this molecule, can you imagine what would happen? Let me go back. I'm drawing all the pictures because we can get bogged down. If I were to stretch this around in a circle, this long line, so that the hydroxyl end could interact with this other end over here, this H over here. Well, we could drop off a few hydrogens because we can always get rid of hydrogens because water is around and it's always going to pull them. So we could make that O right here stick to the carbon right here, and you can see that's what's happening right here. It's formed a loop, right? This is a hexane. Oh no, it's actually, yeah, it is. This is actually a hexane because there's another carbon up here. So in fact, it's reached around. There's another carbon here with its H's to make it hexane. And it's reached around and it's interacted with the second carbon in the chain to sort of make this closed loop. But really, it's the same molecule. And what I want you to see here is that this is the same molecule as that, sort of. It's the same basic idea. These long chains can easily make loops. And because that OH is the reactive site, it's the place where stuff happens, if it bends around on itself, it can have something happen to itself. It can interact with another part of itself, form a chemical bond, and make a loop. Okay, but that's just an aside. Oops, eraser. Okay, so this is our atom. Now, of course, we have to. So what we've got here is we have to fill in the missing bonds, and typically hydrogens would fill those in. But guess what? There's going to be something else. I'm going to put them in red. There's going to be some hydroxyl groups that are attached. One here. One here. Now, when we write it on this side, we write HO. On this side, we write OH. It's the same thing, right? Just because it's bonded to the H. That's still a hydroxyl group. It's just backwards from the back. We're going to have another one attached here. And we're going to have another one attached here. And yet another one attached here. Now, if you count, those carbons only have 3 bonds now. They need 4. So we have to go back then and fill in the H's, right? There'd be one sticking onto that one sort of in the back. This one will have one. Now, of course, this is a 2D model. This molecule in 3D is all caked in bed. And there it is. And this is, of course, called glucose. This is our friend glucose, or an isomer of glucose. Anyway, we'll talk about what that means later. But what I want you to notice is that it contains many hydroxyl groups, which are sites where stuff can happen. Now, is sugar then an alcohol? Well, kind of. We probably would say that once you get past one hydroxyl group, or maybe two, you start to get into something more complicated, and you begin to be classed as a bigger group of things after that. This is actually called a simple sugar now. Glucose isn't called an alcohol as such, even though it does contain many of these hydroxyl groups. Question?
Are all alcohols hydroxyl?
Yes, so every alcohol is going to have a hydroxyl on the end, right? Or somewhere in the middle of the ring. That's what makes them alcohols. They have the hydroxyl group. So all alcohols have hydroxyls, but not everything with hydroxyls is an alcohol. Because the more you get, the more complicated you become, and they give you a new name, they give you a new class. So there's an example of finding the hydroxyl functional group. Now we can kind of buzz through the rest of the functional groups more quickly because we understand kind of the idea. So there are many functional groups, but we're just going to look at the ones in the book. So the next one is called the carbonyl group. So here's what happens here. Let's take some C's and put them in a line. And let's put H's all around. Now we're in red. Okay? Now, this last carbon, let's see what's going to happen. What if the oxygen bonds in a different way? What if the oxygen bonds as a double bond oxygen, which is a possible thing, and then just leaves one H behind? So this looks a little different. There's an O and an H, but they're bonded differently. They're not bonded together. It's not a hydroxyl because the O and the H are separate. So this little section right here, these three in the box, is called a carbonyl. Okay? A carbonyl indicates another class of molecules. For simplicity, what I want to do is first run through all the groups, and then we'll look at the classes later, okay? So you don't get too bogged down and too confused. So identify the carbonyl group. All right, the next one, extend the page, looks like this. If you have carbons and some H's, what would happen if you had lots of oxygen available? Question?
Yeah, I just wanted to ask about the carbonyl group. So it said the two major classes are aldehydes and ketones.
Correct.
And what differentiates them? Is it the hydrogen attached to the carbon?
It's whether or not the carbonyl group occurs on the end of the molecule or in the middle of it.
Okay.
If it's somewhere in the middle, it's a ketone. So we're going to go through all the classes probably tomorrow. Because right now we're just going to identify the groups, and then we'll go into the classes. So I'll give you more detail on that tomorrow. Okay, so watch this now. This time, we're going to have the double bond oxygen, just like we did with the carbonyl group, but we're going to add another OH over here. So now we have two oxygens. That's the difference, right? This one is called carboxyl. Then, of course, the group that this will be linked to later is called the carboxylic acids, another very important biological group of molecules. But for now, just learn to recognize what it looks like, carboxyl. Okay, the next one on your chart is the amino group. So the amino group is kind of important. Put a bunch of carbons here. So you see how I keep drawing this bunch of carbons on the other side? It's sort of like the normal part of the molecule. We sometimes have a shortcut where we just put an R to represent all that stuff. But anyway, we'll get to that later. It's easy. We'll do it this way for now. Okay, now watch what happens to this last carbon. On this last carbon, we attach an N and two H's, like this. So we don't count the carbon, we just count the N and two H's. Obviously, there would have to be two, whoops, wrong color. It would have to be two H's here as well, because this is single bond. But this NH2 thing is called the amino. Okay? Can't read that? It's called the amino group. It is what forms amino acids. Amino acids are acids that have this group. We're going to learn about those shortly. But this is called the amino functional group. Okay? Next, let's do. Did you not see that? All right, go back. There you go. Oops, that's too much. Stop. Ah, what's that all about? There, amino. Hydroxyl, a Y, an O, H-Y, D-R-O, X-Y-L. My O's and A's sometimes get blended together. Hydroxyl. Good to go? Okay, so now we're doing another one. And I think the next one there is phosphate. So this is a very important one too. So what it is it's basically an O attached to a P, and then there's another O, either on the top or the bottom. Now, this book does things a little bit weird, which makes me sort of, it causes confusion, right? So typically, oh, there's a double bond here. I'll finish that. So it's like a cross. It's a P surrounded by O's, and one of them is a double bond. It can be one of these three. It doesn't have to be that. It can't be that one, because O has already got two bonds. But the double bond can occur just about anywhere there if you twist it and bend it. Now, in the book, they put these little minus signs here, like that. What that essentially means is that there used to be a hydrogen there, and it got popped off by water. So that is the same as writing an OH here, like this. Because you can see that that O only has one red bond. It needs another bond, right? O has to have two. And so what they're basically saying in the book is that we have a slightly different name for things. When you write it like this, it's called phosphoric acid. When you write it the other way, it's called phosphate. Anything that ends in ate is basically an acid with some hydrogens popped off. That's what that means. And so you'll often see it written, the way I had it originally, with just the minus signs. When you see those minus signs, just think, oh, that's where a hydrogen used to live, but because of the water dance, it was tugged off, and when it's tugged away, it leaves its electron behind, and it leaves this slightly negative little pole on this molecule. And in this form, in this ion form, it's called phosphate. Okay, so that's what that means. Let's put a box around it here, in black, I guess. This is phosphate. Phosphate. Yeah, that's what I was just talking about. Yes, because if you look at this, though, he's got a double bond, so he could not have an oxygen, because O only has two hands to hold, right? Two valence. And over here, this O is already held. So it's just these guys who seem to only have one bond with the P. So where's the other bond? Well, it was with an H. Or if water pulls the H away, it just keeps the electron, says thank you very much, see you later water, and becomes this ion. Yes? No, not for phosphorus. Because remember, P is different than O. P can form 5. Now, how does it do that? It does it by shuffling its electrons. Remember I told you about hybridization? Remember that these represent the outermost electrons, but there are some underneath in the lower shells. So what it can do is it can grab some of those electrons and kind of use them in bonding, essentially, to create more than 4 bonds. There are many atoms that can do that. But typically, if you look at the periodic table, it's typically the atoms that are lower and more to the right that form more of these 4 and 5. Just like the metals, right? The metals can form ions of valence 2, 3, 4, 7. And it's all because they can shuffle their deck of electrons. And I can't really say more than that until you get your organic chemistry and your grade 12 chemistry under your belt. Okay? All right. So there's one more. I think in your textbook, there's one more group. It's called the sulfhydryl. So let's do that one too. Last one. Sulfhydryl. So here you've got some C's. H, H, H. Hydrogen's attached here.
So, Mr. Brock.
Yep.
Miss Oakley said that she sent an email with the password or something.
Oh, okay, then I'll look for that. This would be an S, a sulfur, attached to an H. So it's an easy one to recognize.
Why does the C have two?
Why does what?
The C has
Which C?
like there's two lines.
Oh, because I screwed up. I went too fast. There. Okay, so this little guy is called sulfhydryl. Ah. Okay. I should have did that in blue. This little group right here is called sulfhydryl, because he's made of sulfur and hydrogen, right? Sulfhydryl. He's the sulfhydryl functional group. And these are the most common functional groups in biology. And they can occur anywhere on a molecule. A molecule could have 1 or 2 or 4 or 5 of these groups. A molecule could have 2 sulfhydryls, a hydroxyl, and an amino. They can have many different combinations of these functional groups. The bigger the molecule, the more places available to stick stuff on, right, for things to happen. Let me go back, though, and show you a couple of things. Are you finished with that one? Just a couple things. Stop. You weren't finished with that one?
So like how much did I miss? Sir, what's your YouTube channel that you're posting this on?
Well, it'll be on the LMS first.
Okay.
And then I have a YouTube channel, but I don't have the playlist set up, so I have to load, you know how it's a lot harder to load on YouTube, it takes more time. And then I have to get the playlist going, so.
Also, sir, are you sure you don't have an email with our password?
Yes, I do, we were talking about that. You guys are, okay, so this big molecule that I've written here, I'm just gonna sort of operate over here. This is pertaining to this guy up here, okay? We could write him, he's got 1, 2, 3, 4, 5 C's. And around those C's, there are H's. So I could write C5, whoops, C5. And if you count the H's, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, not counting this one. There's 11 without him. So C5, H11, and then OH on the end. So you see, we write the functional group separate. We don't put it in the count, so that if you see that, you can immediately identify. But you could also write C5, H12, O, and put the H in there. All the different ways of representing this molecule. This way doesn't tell us much, so it's not as commonly used. This way is far more common because it points out the functional group. But as the numbers add up, obviously, right? The H's are all there. So you can draw the whole picture. You can draw one of these pictures, and it's all the same thing. Okay? Down the line here, the Carbonyl. So let's do this one. I could have written C4, because there are 4 C's, right? Actually, no, I would write C3, sorry, because this is part of the functional group. This carbon here is in the box. So what I would write is, what just happened there? Okay, let's go back. This smartboard it's either very smart and it's purposely screwing us up, or it's not very smart. So I could write, eraser, I could write these 3 C's, which I just erased, C3, Okay, we better put them back so we know what we're talking about. And then I could write COH on the end as the carbonyl functional group. Whatever's in the box, you write on the end. Oh, no, sorry. Oh, see, I'm trying to go fast, and you should never try to go fast. H7 first, right. You gotta put those H's in. CH7, COH. So let's put COH there. Good. So that's another way to write it. Or we could include this H in the count as C3H8CO, which looks weird. You probably would never do that. You could also, what you probably would do instead is put the C in the count as well and write it as C4H8O. Remember glucose, C6H12O6? It's written in this form. Right? And that's because in glucose, there's too many OHs to write this way. But if it's a simple molecule, it's usually written more like this. So it all depends on how big the molecule is, and this is why organic chemistry is such a pain, because there's so many different ways to do it. The carbonyl, the carboxyl, so this one could be written as C3, outside the box. There are 7 H's, H7, and then COOH. That's how we write it. Even though these O's are not bonded together, we still write it this way because we just, as a shortcut, know what that means. So that's another organic chemistry shortcut, right? And you can make this shortcut for all of them. The amino shortcut can be written as NH2. That's what it is. It's 2 H's in N. So this could be C3, H7, and then NH2 written on the end as the functional group, like that. And then the phosphate is the PO4. I know I'm going fast, but it's pretty obvious, and you probably go back figure this out on your own. C3, H7, PO4. Okay? And then sulfhydryl, C3H7SH. So you can also write them in that short form. That's all I'm going to do. Yes, sir?
Did you put PO4 or PO4?
Good question. Typically, when we write this as a molecule, he's asking whether or not you should put 2 minus here because of these guys. Well, it all depends. If this molecule is in water, it's going to occur like this. But when we use the word phosphate, that's what we mean. So if this is the phosphate group, we automatically understand that it has those H's that pop on and off. And so we don't usually write the 2 minus there because it confuses things. We usually just write it as PO4, but we understand how it works. There's lots of shortcuts, right, in organic chemistry. So that's kind of what's going on here. Okay, so these are the main functional groups. You can read the page 26. You can do that. I have a worksheet to give you to practice. It's basically a bunch of worksheets, actually.
That means break.
And so now what I'll do is you can take a break, and I'm going to hand these out to you. When you come back, you can go through them and you can answer the questions as best you can. If you come across something that we didn't cover, try to figure it out by Google. Question?
Yeah, for the carboxyl, would you put like the O's too?
No, because the O's are not bonded together. And that would mean they would be. If you put O2, they would have to be. So I'm going to say no on that. You're welcome. You did double side ones? Did you get 4 pages or 3 pages? No, I thought, did you get 4? Yes. No, that's a totally different example. That has nothing to do with that. This can form a ring. So what we did is we did a different ring with 6 parts. instead. Different examples. Yes. And on that chart, grab one and let me know what numbers you get. Okay, what is it? I forgot to pause the video.